Okay, let's get started. So today, so we just step back one and then do some kind of it's kind of elementary one, but it's some students seems like do not learn this one, so it's and then deflection of light. So these two so these three are very famous for the testing GR, actually, test of GR. And also number 4 is the motion. Motion of black hole. So these are the topic we will cover at least the beginning. I don't know how fast I'm going to do that because some of them are already familiar with this concept. Some, if not, it's better to learn because it's a very basic in GR. So those are I'm going to talk about today. If possible, that I will talk about so-called Volkov theorem. After that, I'll move on to the theorem. So that's what we're going to cover today. Anyway, so these are very, very basic. I think once you find a solution, again, it's better to understand what's physical meaning, what's the physical consequence of that. And that's one of the purpose of this today's lecture. Okay, and then, by the way, so there's how to say, the class on Sunday this week because of this how to say 放假跳课. So this I forgot 国庆节的 anyway. So we need to adjust the class schedule. So this Sunday, so which means that a day after tomorrow, we will have the class again, the same time, same room. And after on Sunday, I'm going to talk about this Kerr black hole. Kerr black hole, there are lots of concepts that we need to cover. Kerr black hole is worth explaining more than one lecture, at least one lecture, maybe more than one lecture. That's the plan of this course. As I mentioned, I promise you to a little bit slow down and then explore a bit more physical concepts. So that's why I'm going to explain these concepts. Okay, what is the gravitational concept? Redshift, consequence of this Schwarzschild geometry. One of the consequences is the gravitational redshift. So redshift, so if you have a star, you have some star or whatever, black hole, whatever is okay, star, and then there is some whatever radius point A, and then omit the electromagnetic wave and receive B. Okay, receive the person at B here. The distance is something like distance is the small b. Okay, so radius is b, and then due to the if the curve is how to say, the space-time is curved or warped, there is some consequence because of the curvature or metric, whatever you call it, t. So suppose so this is x or r. This is A and this is B. Okay, so then and suppose the electromagnetic wave will be how to say will be, so as we know, so it's like a electromagnetic wave is the some kind of how to say, the like this kind of sine wave or cosine wave, whatever you call it, depends on the same thing, sine omega t. Okay. So you have a just some wave with the frequency omega, whatever you call it. Then what you can see is that this the period. So one period is this distance is given by delta t. So here you have a world line of the observer A, and the world line of the observer B, and I should call it small b, and then we measure the time delta t around here. Okay. Fine. Delta t here. If there is no gravitational field, the time of the delta t will be this will give you the frequency if there is no gravitational field. But in any case, so a local observer, you can just consider that this is the frequency. But here, if you have the so the light will travel along with the speed of light, and then you just receive observer B will receive the same. So this distance should be the same because of the speed of light do not it's the same world line. Okay, world line of the light like this way. Okay, but however, if the period of the light is in the presence of gravitational field, the period of light is at the point A will be measured by the proper time, which is minus g00, and then point A, and delta t, and delta tau b is given by the presence of the gravitational field. You have like this way. Sorry, delta t. Okay, delta t. So that's how you obtain this one. So therefore, if you compare the frequency at the nu A and the nu B, which is inversely proportional to the proper time, and so therefore that will give you the ratio of the G00 component of the metric. So I think it should be B 0 and A like this way. Then 1 minus RG B 1 minus RG of A, and the square root like this in the Schwarzschild metric. So therefore, if the radius will be different, and if B is larger, this will be this would be greater than 1, right? This would be greater than 1. Is it true? B is bigger, so this is numerator is bigger than denominator, so therefore this is. So therefore it's nu B is smaller than nu A, which means the gravitational some redshift or Doppler effect, or whatever you call it. And this one is already measured by 1960 by Pound and then Levick experimentally by using gamma rays. Okay, so those are the consequence of the gravitational left shift. It's very simple, but it's one consequence of the gravitational effect. So another thing is that the so it's oh my goodness. Is it the no. Sorry, I thought I learned this one, but I already. I mean, this one is really perihelion precession. It's really like kind of like a unfamiliar English. I'm familiar with English, so okay. Okay, so this one. Mercury is the Schwarzschild. Okay. So that's the second consequence of the we will consider for the in Newton mechanics. We know that the planet will orbit. It become ellipsoid. So ellipsoid. I don't know. I mean, ellipsoid is something like this way, and then here like this way. Like this way, and there's some okay, center is here, and then here you have A1 minus E. This is A1 plus E, okay, and E is called eccentricity. How to say? Is it called? I don't know. How do you call it in Japanese, I think like this way. I'm I don't know. Eccentricity? I forgot how to write that. Even in English, I don't remember how to write. I think in the lecture note I wrote somewhere. I think eccentricity. E is eccentricity. Anyway, so that will give you the ratio between this one and then this one. Okay. So you understand what I meant. Ellipsoid. Essentially, you just fix 2 points, and then the sum of the lengths should be the same, right? So one of the points should be the center of the sun or whatever. Sun and then planet is ellipsoid, and the ratio will be given by E. Okay. Is it in Chinese the same? Or it's same? Okay, then we can communicate by writing. Okay. I'm just eccentricity is okay. Okay. Fine. But however, so this perihelion is in fact the point the which close the closest point. So this is I think you can easily see from here, right? So this perihelion is here. But however, if there is a gravitational effect, we will see that there is something. So this point will move actually. This point, I mean, graph as I mentioned last time. So it becomes something this kind of movement will occur. So the eccentricity. So this perihelion will move like this way. Anyway, like this way. My drawing is horrible, but anyway, it will move like this way. So we will see from the metric. Okay, and the action of the this planet motion it will be given by like this way. G mu nu, x mu dot, like this one. And then, so here I use the proper time. Is the dot is the derivative with respect to proper time is like this way. And then this will give you the if you write down in the Schwarzschild metric RG over R inverse and then x dot 0 square plus 1 minus rg over r inverse r dot square. And then r square theta dot square plus sine square phi dot square, like this way. So these are the action we have, okay? And then what we're going to do is that we see that the theta is equal to pi over 2. So we only look at the xy plane, not the this is x, this is y, and so we just only focus on the xy plane. So the theta, we can fix the theta equal to pi over 2. So this term will be gone. So this term will be gone. And then this one become 1. This one become 1. And then we just derive the equation motion for the planet. Okay. It's so for instance variation. So variation of x naught will give you dd tau and the 1 minus rg over r over x naught dot equal to 0, which can be easily seen. So you just do the variation with this respect to x naught. Anyway, so you will get this one, but this is the Euler Lagrange equation, as you can easily see. I mean, just integral parts or whatever you call. And this means that we can just consider that the 1 minus rg over r of dt and d tau is equal to epsilon, which is constant. Okay, so this is the one consequence. Okay, and then another equation of motion is that the dd tau, so variation with respect to phi will give you dd tau. Wow, the r square phi dot is equal to 0. So therefore, phi dot r square is equal to constant. Okay, constant. This is a constant. Okay, so this corresponding to the what in the classical mechanics? Yeah, this is angular momentum, and this corresponds to like kind of energy, as we will see. Like you need to somehow make some shift and some change, but this is related to energy of the prime. Okay. Good. Fine. So now instead of dot, we introduce prime, which is the dr d phi. Okay. So this is dr d phi is equal to r dot divided by phi dot. And this is equal to r square over L r square, r dot. Okay, so that's I use this one to write this. Okay, so then we can just do the so we know so here tau is the proper time. So the proper time is so. We can just write down rg over r, and then what was that? X dot 0 square inverse r dot square plus r square, and then plus L square over r square. Okay. So here, so I use the so d tau square is equal to g mu nu x mu dx nu, and then most likely I need a minus sign here, and then I don't like c, but somehow I still pick c squared, like this way. And then you will get this one. And plug this one, this equation, plug this equation into here, 1 minus rg over r, and the x0 dot square is coming from here, so plug this one into here. Okay, and then what you obtain is as follows. So what you obtain is the 1 minus is equal to 1 minus rg over r inverse, and the e square minus l square over c square, r prime over r square minus l square, c square, r square. Okay, that's what you obtain as an equation. Okay, so this is the equation for the r. Okay, so r is the r is a function of phi and then somehow phi, and so here this equation will give you the r is a function of phi somehow. Okay, so let's slightly massage this equation as follows. We define u is defined 1 over r, and then u prime is again is a derivative with respect to phi. Then this equation can be written as follows: u prime square plus u square minus rg c square over l square u minus 2e over l square is equal rg u cube. E is equal to c square e square minus 1. Okay. So this is the definition. Okay. It's just rewriting this equation like this way. Fine. And here, so if you are really astute audience, you realize that in fact this one, if you forget about this one, this is actually if you forget about this equation, this one is indeed equal to the Newtonian equation. To see a bit more clearly, bit more clearly, we will take further derivative with respect to phi. So if you take the dd phi, derivative dd phi, and this equation become like this way. U double prime u minus 1 over a is equal to 3 over 2 rg. Okay, so that's what you get. Where a I define as the L square over Gn. Okay, Gn. And if you forget about this right hand side, and solve this equation, if you solve this equation, u can be understood as u can be solved like this way: 1 over a, 1 plus e cos phi. So if you plug this one into here, you can easily see that this equation is equal to 0. Okay, I mean you can just do the calculation immediately. That for instance, if you take a derivative of the two derivatives, you get the minus e times cosine phi, right? But if you count u minus 1 over a is 1 over, so one part is cancel, and this part will cancel. Okay, do you understand? Okay, so therefore this is the equation, and this is in fact the equation for ellipsoid. Okay, this is indeed a is exactly the a written here, E is the eccentricity here. Fine. So E can be understood as some kind of integration constant and so on. Okay. Fine, but we have some correction due to the GR. Okay, so this GR, so right hand side is a GR correction to the Newtonian mechanics. So therefore we need to somehow we need some kind of correction to this ellipsoid, beautiful ellipsoid. And to find a solution to this including GR effect, we use some kind of ansatz. So suppose this effect is very small, and then so that if this is effect is very small, the orbit is almost like an ellipsoid, right? It should be almost like an ellipsoid. So therefore, we just use ansatz. So this is Newton. This is Newton. This is you can derive them from Newtonian mechanics. But here, so ansatz is the almost same, which means A1 plus E cos 1 minus eta phi. So suppose eta is very small. Suppose eta is small. And there is some collection plus eta plus alpha plus beta. So this is ansatz, cos 2 phi. Like this. So this is the ansatz we make. Suppose the solution, we would take this form. So eta is very small. If you take eta goes to 0, it recover Newton equation. Fine. And then so ansatz, the beauty of ansatz is just you can easily compute. So just put this one into here. Put this way, it's a bit ad hoc. Then left hand side become like this way. 1 over A, eta, and then 2E cos 1 minus eta phi plus alpha plus 3 beta. It's just consequence of, I only take the leading order of the eta. Phi and plus order eta squared. I just take the leading order. And right hand side is super simple. Right hand side, wait. There is something strange here. Why it should. Huh? There's something strange here. What's going on? Plug this one into here. I think something I made a mistake, of which I don't know. Let me check what the mistake is. Sorry. Wait. I think I made a mistake. Sorry, I think I missed U square. Yeah. Sorry, I think I missed U square because dimension is somewhere. E, I think I'm double prime U is, yeah, I think I missed U square here. Sorry, it should be U square. Yeah, sorry. So I think I missed U square. So let's do calculation. I think it's super easy. If you take d phi, you get a 2u double prime, right? And then 2u prime, and then here also u prime, rg, c square, l square, u prime. And this is gone, and the rg, 3, u square, u double prime, right? U prime, sorry, u prime. Okay, and then u prime somehow can be erased by using this equation. And plugged out into here, you should get this one. Okay. Sorry, you double. Oh, okay. So it's super easy computation. So u prime you can erase everything. Okay. U prime you can erase everything, and then just divided by 2 will give you this one. So therefore, sorry. So there must be u squared. Sorry. U squared, and then so there's a typo in the lecture note. 3rg divided by 2a squared 1 plus 2e cos 1 minus 8 of 5, and then plus e squared cos squared 1 minus 8 of 5, okay, plus order 8 squared. Okay, so that's what you get. And compare between these two. Okay. So if you compare between these two, what we see is that the first of all, the overall factor should be the same. Where did I put the this one? Overall factor should be the same. So this factor should be the same as this one. So this one, this part will give you eta is equal to 3rg divided by 2a. Okay, so that's what you get. So eta should be 3rg 2a, okay, over 2a. 3rg over 2a. Okay, and plug this one into here. If you compare between these two, so then what you end up with what? So we can just approximate this one is equal to, roughly speaking, cos square 1 minus 8 of 5. So because since eta is, we assume eta is very small, so therefore e square over 6 should be equal to beta. Beta should be, so beta should be equal to minus e square over 6, because I mean just compare these two terms. Beta should be this term, and the 1 should be recovered from this one. So therefore this should be give you alpha is equal to 1 plus e square over 2. Okay. So those are the equation you will get. And then plug this one into here. Plug this one into here. This is the approximate solution of this the equation, including gravitation, GR effect. So including right hand side. Okay, right hand side. Fine. And what's the consequence of this one? Consequence is that what are the consequence? Consequence is that here you have some shift, or whatever, 1 minus 8 times 5, not simply 5. So therefore, the 2 pi rotation is not enough, okay? To get this 进入点, no 进入点. Sorry, my tone is horrible. So therefore, what's really happening is that so to get this perihelion, perihelion, what you need to do is that you need an extra rotation. Okay. So the total change of period is no longer 2 pi. 2 pi, we need a 2 pi plus 2 pi eta. Okay, so you need a 2 pi eta to cancel minus 8. Okay. And as you can easily see from this analysis, Eta is the RG over A. Okay, A is very big because it's just a kind of radius of the this planet motion. On the other hand, RG is a Schwarzschild radius of the sun. Okay, so as I mentioned, RG of the Schwarzschild radius of sun is that 2 to 3 kilometer. I don't remember when. I think 3 kilometer. In my first lecture, I mentioned 2 kilometer, but that's not correct. Maybe 3 kilometer. But anyway, it's very small. It's just 3 kilometer is just going to like a Handan campus, less than Handan campus. But A is kind of like the distance to sun, right? So okay, distance. So A is very small. Okay. So our estimate is very correct. So to see this effect, so you need A should be very small, okay? And so therefore, what we need to use is the best candidate to probe this 进入点进洞. Anyway, perihelion precession is that the best candidate is the planet which is closest to the sun, which is Mercury, okay? So A, we want the candidate A is the smallest in our planet, okay? And that one is the Mercury, okay? So in the case of Mercury, here, so we can make an estimate. So we know A is equal to that one, so A is equal to 3G squared M squared over C squared L squared. So I just restore the A and RG by using that one, and you get this. Okay. So then, so this is equal to 3G squared, or maybe you can restore 2 pi, and 2 pi, 3G squared M squared divided by C squared L GM 1 minus E squared. So L is in fact equal to the, L is a distance, the longer distance. This is, I call it L, which is the A over 1 plus E plus A over 1 minus E, which is A minus 1 minus E squared. Okay. So I plug it into here, you can obtain this. And then you can easily see that this one cancel with this one. Okay. So what end up is the 6 pi. Like this way. Okay. Like this way. Fine. And then all those values are, you can easily find the correct the value of the Mercury. So in the case of Mercury, or say, and then this is equal to, roughly speaking, 5 times 10 to the minus 7 rad. Okay. Which means that it will change 43.03 seconds per century. 1 century, 100 years. Okay. So only this amount will change. Okay. It's very small, tiny correction, but this one is already experimentally verified. Fine. So this is the consequence of the. So this is the GR effect. This is the GR effect. Consequence effect. Any question at this moment? very nice. So then another consequence is the deflection of light. Deflection of light. Another consequence is deflection of light. So deflection of light is at the so let's see. So if you have this axis like this way, and then here you have something like there is a black hole, star, or whatever. You have the whatever, the star or black hole, or you have it. Then I think you are observer around here, Okay, observer here, and then star is around here. So then what's really happening is that the there is some star is just emitting how to say, like this way, emitting the light electromagnetic wave or whatever. It's a slightly ugly. Like this way, maybe. Anyway. So due to the gravitational effect, somehow the bending of light will occur. And then so observer here, sitting here, is that the star is essentially is located. This is the apparent position. Apparent position. And this is a real position. So this is the effect of the gravitational effect. So light will be bending so that the observer is like a star is look like sitting here, but in fact the position is different. Fine. So this is the effect, and what we want is to measure is something like we want to measure the angle alpha. This is alpha. Okay. Angle alpha here. So the alpha, this round angle, yeah, is we want to measure in terms of the path around this delta. I call it delta here. So the question is, what's the relation between alpha and the delta? What is the relation? Okay, so that's what we want to see from the gravitational effect. So we want to estimate this one. To do that, I mean, again, we just solve the equation of motion for light. Okay, but we cannot use the proper time for derivative, because I mean d tau square is equal to 0 for light. Okay, d tau square is equal to light, but we can just use whatever coordinate whatever parameter we can use. Then what you end up with is, unfortunately, I already erased. Is the so what we have is that the equation is 0, now 0, because of the d tau square is equal to 0. So the proper length, proper time is for light is 0 by x0 of Rg of R and x0 dot square. So now dot is some other kind of parameter. So here lambda, I call it lambda, is the some kind of parameter that measure the trajectory of light. Okay, so that now x mu is the function of lambda. Okay, then the rest of the computation is the same. Okay, so that's what we had. So again, I said the theta is equal to 2 pi over 2 without loss of generality. So we just place everything over the xy plane here. Okay, xy plane here. And then solve the equation. Again, so this is the equation motion. Again, then you have this angular momentum conservation and also some kind of energy conservation. dt over d lambda is equal to AC. Fine. Yeah, tau dot over epsilon, like this. Fine. And they plugged everything back to here. What you get is as follows. Again, u double prime square plus u square minus delta square is equal to rg over rg u cube. U is again 1 over r, and delta is some ratio between angular momentum and epsilon. So these are the solution. No, the equation for this one. So plug this one into here, and plug this one into here, and do the manipulation. Okay. Do the manipulation. Again, phi dot, u dot is the derivative. U prime is with respect to derivative of phi. Okay, bar phi. Fine. And again, so as I mentioned, so this guy is the GR effect. This is in fact the same as above. So this is GR effect. GR effect. But if you ignore this term, one can solve this equation so easily. If you ignore this term, so this is Newton. Newton case is ignoring this one. The equation is u is equal to 1 over delta cos phi. Okay, cos phi. So if you plug this one into left hand side, you can easily see this is solution. Can you see that? Can you see this? So if you plug this one, you will get the 1 over delta square sine square phi. Why is that? Okay, so minus sign is missing. Okay, minus sign missing. So now it's okay, right? And then plus cos phi square is equal to 1 over delta square. Okay. So therefore, this, if you ignore the right hand side, this is the solution. Okay, this is the solution. What does it mean? U is 1 over r. So this means that this r is equal to delta divided by cos phi, right? Cos phi. Okay. So which means that if you start the light from delta distance, you just go straight parallel. Do you understand? R is a distance. R is a distance like whatever. I can use some other color. Is it purple? R is a distance from like this way, right? R is a distance like this way. And phi is the, whatever phi is okay. I mean, phi is the, R is a distance like this way, and phi is the phi is something like this one, okay? My R times cosine phi is here, right? Here, right? Which is delta, so it's okay. So it's just that in Newton mechanics, light goes straight. That's it. There's no gravitational effect. Okay. But if you include this one, I think again we need to have some correction. So let's make an estimate for this correction. And to do that again, we will do the assumption. So again, ansatz. So again, we make an ansatz. Ansatz is so the correction is very small, which is 1 over delta cos phi, plus some kind of function or chi of phi. And plug this one into the equation here. Okay. Okay. So then what you get is that so what you get is a chi. If you plug that into here, chi is equal to Rg over delta. I mean, this one you can easily solve by using, even this one you can do analytically. Plus constant times sine phi. Some number times sine phi. So you can easily solve by this equation. Okay. Like this way. Okay, so then plug into here, what you get is the 1 over r. Delta. Okay, like this way, fine. If you plug this one into here, you get this one. So I just so we can choose this one to be 0 if so this is symmetric. So this diffraction is very symmetric. If you take this is symmetric, deflection is symmetric. This time you can take Z. So this is the answer. And let's see how the bending will look like. So when R goes to infinity, R goes to infinity is really, R goes to infinity is like this yellow line goes to the really close to this axis. Okay, close to this axis. In this case, the angle phi is almost, so phi is pi over 2 plus minus. Phi is here. Sorry, phi is this one. Sorry, phi is here. Right? Cosine is this divided by this one, right? Yeah, it's okay. Yeah, this over this one. So okay, phi is this one. So therefore, R goes to infinity, phi should be either minus pi over 2 or plus pi over 2. Okay? And there is some correction because of the plus alpha. Okay. Plus alpha, where the alpha is very small. Alpha is very small. Okay. So as you can easily see, so R goes to infinity, left hand side 0, right? And if you plug pi over 2 to the Newtonian equation, cosine pi over 2 is 0, right? Cosine pi over 2 is 0. So 0 is equal to 0, right? So it's okay. So if you ignore this term. But there is some correction because of the second term, okay? And then we can make an estimate for this one. And if plugging that one into here, which means that 0 is equal to delta over pi cos pi over 2 plus alpha and plus RG over 2 delta square 1 plus sine square pi over 2 plus alpha. Okay, so that's the case. And you can take only leading order term. So we can just take the leading order equation for in alpha. What is the leading order for this one? Yeah, most likely this one should be equal to. Can you do the? Can you solve? And this one will give you alpha is roughly Rg over delta. So that's what you get. I think from here you can only have the sine pi over 2 plus x is equal to what? Minus cosine? Is it correct? Is it correct? Huh? Is it correct?
There is no minus.
So this is sine curve, right? And then pi over, oh, there is no minus. Okay, thank you. So this one is 1 plus x squared over 2 plus x4, right? Over 4 factorial. Is it correct? Minus. Okay. And then cos pi over 2. No, I just try to wake you up. Cos pi over 2 plus x is the sine x. Is it minus sine x? And then this one is equal to minus 1, no, 0. This is x plus x minus x cubed over 3 factorial, like this way. Is it okay? You plug that into here. What you get is what? 0 is equal to 1 over delta minus alpha plus Rg delta square 2. And then here you have a 2 plus whatever alpha square some number, but if we ignore this one, so the 2 cancel, and you get this one. Okay, fine. Is everything okay? Is it okay? Is my calculation okay? I hope you understand. So we ignore alpha square term, and so this equals to 0 means the alpha is like this. Fine. And again, delta, what is delta? Delta is defined where? Did I define delta? Unfortunately, erase. Delta is equal to L square, L over E over C square, C. Okay. So delta is very big, very big. I mean, you can easily see. I mean, delta can be very. Yeah, I mean, we will see what kind of delta you can take. This it depends, but I mean it's the usual diffraction of light occur. But if you go too closely to the black hole, I mean, of course, if you hit the Schwarzschild, it enters the black hole. You can never see. Also, from now on, we will make an estimate, but if it is close, but you make a kind of like a spiral into the black hole, or like make an orbital moment or deflection, light will occur. Anyway, so we will make an estimate of what kind of delta we should take. But if you consider this one like a very small, in the case of our planet, it's of course very very small. So for instance, if you consider the situation like sun. If you consider our sun, delta should be radius of the sun, right? Delta should be radius sun. Is at best we can do. So there's a sun, and then there's some whatever. My how to say solar eclipse in the solar eclipse in Chinese? I don't know. Even is it same? Eclipse. Is it same? And then total solar eclipse is even Japanese. I don't remember. Anyway, if the moon covers the sun, anyway, moon covers sun, so you can seal the light of sun, right? Then if there is some light coming from really close to the sun, almost radius of our almost plus something, you can still measure the light. Okay? Because you can see the moon see the sunlight, so that if there is something coming from the outside of the sun, or slightly way out from you can still measure. So the alpha delta here can be the size of the radius of the sun. But as I mentioned, this one is very big. I don't know the radius sun. I don't know. I think you can just search. And then the RG is again 3 kilometers for sun. So if you use our sun to measure this deflection light, this RG over delta is very small. Okay, very small. And then in the case, it's written here. It's written RG is around 7 times 10 to the 5 kilometer. So therefore alpha is something like a 2 times 3 divided by 7 times 10 to the 5, which is 1.75 second. Okay. And then this one is also experimentally proved when the total solar eclipse. Okay, so that's what's really happening for this. Okay, so we see that one is the redshift. Oh my goodness, is it it's my Chinese lesson. And number 2 is what was that? Mercury preheat. Okay. 进入电进动. And number 3 is what was that? Deflection light. This one for me it's hopeless. Is it like this way? It's just Is it correct? Anyway, it's just my Chinese lesson. Sorry about it. Oh yeah, this is not like this way. Like this way. Okay. Guandai. Maybe in Li. Okay. So those are the most famous tests of the GR. Test of GR. So we quickly review by using like 1 over and so on. Okay, let's take a quick break and then we'll move on to the motion of okay. Before that, I will make it just a summary. Anyway, I wouldn't say summary. So if you have a black hole, there is some singularity r equal to 0, and then Schwarzschild RG is here, Schwarzschild radius. And then if it is the far away, you can just escape from the. So now, so here we always have. Yeah. So we assume the phi dot is whatever. R squared is equal to L. And then, so as we will see that we will see at some point, if the light comes very close enough, so it eventually captured in the black hole, like this way, taking spiral. At some point, you can just have a deflection of light, or some planet can escape to the infinity. And also, we can see that at some point, you can just have an orbit. You can have an orbit like this way. You can also have orbit like this way. We can make an estimate depending on the radius r and depending on the angular momentum L and also energy. Using this relation, we can find how the particle around the black hole behave by using this, again, equation motion. Anyway, so let's take a 10 or 15 minutes break, and then let's talk about this one. Fine. How do you write the total solar eclipse in Chinese? Oh. How do you write? Oh, I see. Then it's different from Japanese. In Japanese, like this way. I think this is the Japanese. Yeah. No. What? Yeah, this is Japanese. Okay, so this is the Chinese. Okay.
I will ask.
Okay.
What's the initial force affect the Einstein equation?
Initial force. What do you mean?
Inertial force.
Which object?
Like in accelerating object of free.
Oh. Can you make the question a bit more concrete? Which system are you thinking about? Which system are you thinking about? Is it Schwarzschild or somewhere else, or which whatever? Okay, rotating system. Is it the
in classic
classical mechanics?
yes, the rotating in the rotating frame there will be like this force and this force.
Okay. Okay.
How does this force
In GR?
Yes.
Oh, okay. I will explain from now.
Oh,
Yeah. So after the break, I will explain how it works here.
oh.
Yeah. How does this potential look like? Okay, I think there are lots of mistakes in lecture note. I mean, if you find something strange in lecture note, let me know. Let me change the one I made a mistake. U square. Okay, then shall we resume? Okay, now so let's examine the let's examine the motion of the particle, whatever, around the black hole. This is important for observational reason, even though it's a Schwarzschild. Schwarzschild. I mean, most of the star is you need to use the car, but it's a good exercise before going to car to use the Schwarzschild to do this kind of exercise. So this kind of stuff, today you learned these three tests of which you are. How many of you already learned this one before today? Please raise your hand. Okay. Most of them look like. Most of them. Okay. And the motion, I don't know, motion around the black hole. I don't know, do you guys learn this kind of stuff? But let's do the motions around the black hole. So we again set the theta is equal to pi over 2. And then we can have the equation of motion. So equation of motion again Rg over R. I don't know how many times I wrote this one today, but anyway, so it's important to write down them. So it's minus 1 minus Rg over R inverse T dot square plus R square phi dot square is equal to most likely I need to use something is equal to c square. Sorry, this is minus sign, I think, minus sign and a c square. Okay, so this is the c square. Again, dot means the ddt tau, proper time, because we consider particle has some mass, not light. So we consider this kind of system. And then take with respect to the derivative of R, ddr. Oh, sorry. I think I told you completely stupid. Sorry. So this is the action. So you start with this action. It's I and up to some sign. I think it should be okay. And d tau. So this is the action we consider, and then we take variation with respect to R. Okay. Then what you get is Rg over R x dot 0 square plus 1 minus Rg over R minus 2 Rg divided by R square R dot square plus 2R phi dot square. Plus 2R phi dot square plus 2 dd tau 1 minus Rg divided by R inverse R dot. Okay. Equal to 0. Okay. Fine. So we just try to derive first the equation of motion for the. Also, we have the again what was that? The R square angular momentum conservation is equal to L, and then what was that? What else? 1 minus Rg divided by R tau dot is equal to epsilon. So we have this one. So this is kind of energy conservation. Hopefully, so far I don't tell you, right? I think this should be okay. And then we plug this one into this c square is equal to equation motion 1 minus rg over r x dot 0 square minus this one inverse t dot square plus r square phi dot square. Okay. R square phi dot square. Sorry, this is a minus sign, and plug this one into here, and what you get is as follows. What you get is e. Why I wrote t dot here? You should correct me. This is r dot square. You should correct me. This is r dot square. Did I make stupid mistake previously? I mean, if I make a mistake, please point me out. Okay, this is okay, and plug this one into here. Plug this one into here, and then what we get is that the this one, and then this is r square. This one is equal to L square divided by R square, right? This one is L square, and this is equal to E square divided by this one, right? And then most likely we need to scale by whatever, C square or something like that, like this way, 1 minus RG over R, okay? So that's the case. And then we can rewrite this equation as follows. So R dot square divided by 2 plus minus GM over R plus L square over 2R square minus RG L square divided by R cubed over 2 is equal to 1 over 2 C square E square minus 1. Okay. So that's what we get. Okay. Is everything okay? Do you agree with me? Is this computation okay for you guys? I hope it's okay for you guys. I mean, just rewrite this one and plug into this value, okay? And then eliminate phi dot square and x dot square. Okay? And here, which one is Newtonian? So this can be understood as the energy. So we define this one is equal to energy. Define this one as energy. And then here, so here we can just define as a potential, B of R, okay? B of R. Okay. And which one is a Newtonian term? So this is gravitational potential, you can easily see, okay? And what's this? Yeah, this is called centrifugal. I don't know. Forces. Because of angular momentum, you have this kind of like a repulsion because of the repulsion potential because of the because of angular momentum. But here you have a gravitational the GR correction. So this one is not present. So this term is not present in the Newtonian mechanics. This is GR effect correction. Okay. How do you write the centrifugal forces in Chinese? I think. Is it the in Japanese this one? Is it same? 原性不一样，好像不一样。Okay, so somehow, what did you say? In Chinese, how do?
离心力。
离 is this one.
Yeah.
Oh, I see. Okay. Similar. In Japanese, it's slightly different. 离心力. Okay. Anyway, so those are the potential, and then so the reason why I draw this way is that this equation can be derived even from here. So if you use this relation, so if you use number 1, this is number 1, number 2, and number 3. Number 3, and plug this one into here, what you get is actually derivative of this one. So derivative of this one means if you use this equation, the second derivative of tau, and then minus gm of r square plus l square over r cube minus 3rg l square 2r4 is equal to actually dv dr minus sign. Okay. Is there some mistake? So this is the equation. So if you plug this 1, 2, 3 into here, in fact you will get r derivative, tau derivative of this guy. Okay, derivative of this equation. So this equation essentially means that the r dot square over 2 plus b of r is equal to e. Okay, and you can take derivative with respect to whatever tau of this tau equation. You can derive this one too. Okay, so therefore this equation, or 1 and 2 and 3 and this is 4 are not independent. Okay, but that's anyway. So those are the equation for the particle around the black hole, Schwarzschild black hole, and let's try to solve this equation. Let's try to solve this equation. So we can just write down we can draw this potential very easily. We can draw this potential. So I draw yesterday or whatever. I used Mathematica to draw. This is the B of R, and this is the R. Essentially, it's a combination of 1 over R and 1 over R square and 1 over R cube. Okay, and anyway, so the first one is if you close to the singularity, so this 1 over R cube is the dominant term. Okay, if R goes to 0, 1 over R cube is the dominant part, and you can ignore this one. But if you slightly increase the radius, this term will start making contribution. Okay, and then later this term will make a starting contribution. Okay, so essentially, if you look at sign of this sign of the so 1 over R squared is something like, I don't know that, 1 over R squared term is something like this way, most likely. And so this is a negative sign, as you can easily see. And then 1 over R is something like, I don't know, roughly speaking like this way, maybe. So this is 1 over R. And then this is 1 over R cubed. Okay, R minus 1. And then here, the second term is a plus sign, okay? So plus sign, so therefore it becomes something like Yeah. Like this way. And you have sum the map. Okay? You have sum the map. And then depending on the body of M and L, and so then the shape of the curve potential will be different. And then the threshold for this one is that if the L so is the square root no, sorry. 2 RGC. If this is the case, if L is a 2 greater than 2 RGC, there's always solution of the BR exist solution. BR prime minus is equal to 0. Okay, there is such a solution, which means that the there is something like it becomes like this way, roughly speaking. Fortunately, there is no color, so it becomes like this way. I don't think it will exceed. Sorry, I don't think it will exceed. It will exceed. I don't think it will exceed, but. Like this way. Am I writing correctly? Yeah, I think like this way. I hope I'm correct. Yeah, I hope I'm correct. Like this way. Okay. So this is I call it R minus and R plus. Okay. So there is a solution B of R. So first the dominant part is R to the minus 3, and the R to the minus 2 starts contributing. And if the angular momentum is greater than this value, it becomes positive. B of R becomes positive, and they become next negative, and then cross to go to 0. So that's it, like this. Okay. And then if the L is the this value, what was that? 2RG C, and then less than square root 3RG C. They exist R max and R min. Okay. So, which means that the there is some. So this is R max, and this is R min, and then if this is the case, the potential never goes to 0. Because this yellow part, the contribution yellow part becomes small when the L is this value, but still have like a maximum and a minimum. Okay. So therefore, unfortunately, I have to erase this kind of stuff. I hope what I'm doing is understandable, even if after I erase. Okay, so around this values, the curve become like this way. Like this way. Okay, curve become like this way. So R max is some anyway. So this is R max and R min, and then it eventually goes to 0. Okay, goes to 0. But however, L is less than square root 3 RG. There is no, like, it's monotonically increasing, monotonically. So it becomes like this way. Like this way. So those are behavior one can plot, and then yesterday I plot using Mathematica. Anyway, it's hard to see this kind of like a, how to say, valley. I mean, this diagram is kind of exaggerated now. Okay, exaggerated. Okay, so that's the case. And then here it's kind of like there exists an R max and R min, and this in this region monotonically increasing. Okay, so those are the fine. So the behavior, okay, and then let me write down the so case A, case B, case C. So these are the interesting. I don't know. Case A and case B are the behavior is almost similar, but yeah. Okay. So number C, case C is the so the simplest numbers case C. So here is angular momentum. Momentum L is too small to escape from black hole. Okay. So you start with whatever R goes to infinity, and just close to the approaching the black hole. It inevitably goes to this hits the singularity. Okay, so if angular momentum too small, whatever, there is a R equal to 0 and the R equal to G. If it is angular momentum too small and it just monotonically goes to the area. Absorbed into the number B and case A and case B are almost same, but anyway, so okay, case A or case B and case A are almost similar. It's just you have to shift the energy level and are as follows. So I will write down the very rough figure. It's an exaggerated one. So exaggerated one is exaggerated figure like this way. So exaggerated figure. So actually this is not it's a very exaggerated figure. But to capture the physics, I will exaggerate. So if energy is the greater than the R max, okay? The initial energy moving toward to the black hole, it inevitably hits into the black hole singularity. However, if the energy is smaller than the B R max, so it just hits to the potential and went back. Okay, went back. Go back. Go back. So this means that I can erase. So in the case of the second case, the first case, the one is like a really the initial RG is too strong that eventually like I think this is not good way. Anyway, so it's just eventually absorbed like this way. So this is the first case. The second case is that the maybe I should use a different color. Yeah. So second case, the energy is smaller than B max. So therefore, I call it this one is the yellow one. B R max. So then I think I call it this one is the roughly this position is R star. Then the behavior is something like this one. This is R star, and then something like this one maybe like this one. Anyway, so this R star is the closest part, but you can just move away from the black hole. So this kind of deflection occurs, but this is the case. And then another case is you can trap by well of the maybe I can use the some other color. Okay. Anyway, so the some other color trap by this is E is the how do you write? E is less than 0 and greater than B R min. Okay, so in this case, number A. So I just wrote like this way. Number A is like this way. Then there is some potential well, so that there is some kind of like how to say orbit motion will happen. I don't know. It depends on so there may be some kind of like precession, but essentially what's happening is that I don't know. It's hard to draw, but something like this kind of like an ellipsoid type. Even though there may be some precession occurs because of the gravitational effect, like this way. Anyway, so this orbital, so this will give you orbital motion. Orbital motion. Okay. So it's trapped by the potential one. Okay. So that's what's really happening. So in the case of B, it's kind of like so this line is shifted above, but it's the same thing. I mean, it's the same thing happen. But there is some particular point. You can see that the particular point at the maxima and minima. That is a particular some state. So this is unstable. So this point is unstable. Unstable. This is stable. Circular orbit. It's a circular. R never change. Okay. So it becomes really circular. Which means that it becomes really circular like this way. Anyway, some drawing horrible, but so this is stable, but this one is very unstable. Once you change, perturb a little bit, either how to say, goes to the singularity or go to infinity. Okay, go to infinity. So that's what's really happening. Fine. So those are the effect. So the difference between, so as I mentioned last, the difference is literally this term. So what we have, unfortunately I erased, in Newton mechanics, it always went to the, Newton mechanics, there is no R, 1 over R cubed term. So therefore, all the potential, so will eventually are this 力性力 will win against the gravitational what was it? Attraction. So therefore, always there is something the figure should be something like in Newtonian mechanics, figure should be something like always like this way. Always like this way. This is Newton. Okay, Newton mechanics. So if your R is very small enough, this angular momentum repulsion will win against the gravitational attraction. So therefore, there must be something. It never hits the organs of zero if you have angular momentum. Okay, but the difference between Schwarzschild or GR effect, if you include GR effect, there is a 1 over R cubed part will show up. So therefore, it can enter then. So the difference is something like a B of R is 1 over G of M over R plus R squared L squared plus minus, I already forgot, something like R cubed. There's some factor is missing. I don't remember. What was it? Yeah, 2 and then square 3, like this way. So this factor is very important that so that they eventually it hits to the singularity if the energy is high enough. Okay, high enough. So therefore that's a crucial difference between Newton mechanics and the GR. Okay, so this term will become dominant when R goes to 0. Okay, that's the point. Okay. And of course, if you enter the enter the RG equals to 0, of course the light cone is we already learned this one, but light cone become like this way, so it never come back. Any question at this moment? Is it so far so good? Too easy for you guys? Anyway, so repetition is a mother of learning, so it's okay to review once more. If there is no question, I can talk about some kind of cross section of the black hole. Where should I erase? Maybe here. Cross section of black hole. Do you have any question? Do you learn this kind of stuff in the GR? I hope you learn. But I don't know. Recently, do Edu teach GR? Seems like no. Always Cosmo teaches, and the Cosmo always use these same slides and so on every year, as far as I heard. Okay. And most likely you never learn this kind of stuff from Cosmo class, so it's meaningful to review this one. Fine. Let's compute the cross section. So what is the cross section? So we start with the whatever XY axis. So this is X and Y. And there's a black hole, Schwarzschild RG. So this is the RG. And we so we put some particle which is not some particle at the infinity with radius r star, okay, r star with or distance r. I mean, I wouldn't say radius because I mean distance y-axis, or let's go y star, and the initial is almost, the speed is almost the same as the speed of light. So therefore, the energy is almost infinity, and we will see what's going to happen. So we just send the particle in the infinite energy, and what's going to happen eventually to if this distance is the big enough, it becomes like this way. It becomes like this way. It becomes like this way. And if it is gradually close to the Schwarzschild radius, it becomes sometimes something like this way, maybe like this way. This can occur, but whatever. This can occur. Okay. This can occur but if you just y star is getting smaller and smaller, it's smaller and smaller at the end of the day. So the eventually trapped by black hole. Okay, and the question is, what is the critical value of y star? So that the particle of the infinite energy will be captured into the black hole. Okay, so we want to measure what critical value of y star. If this is the y is the slightly bigger than y star, somehow you can escape if you use the infinite energy. Okay, but if it is less than y star, inevitably captured by black hole. Okay, so that's the critical value we want to evaluate. So that's what we want to evaluate. So the black hole cross section is essentially pi y square. So that's what we want to y star square. That is critical value. So this is a black hole cross section. Okay. So that's what we want to evaluate. Okay, so to evaluate this one, what shall we do? We want to differentiate this. Okay, what should we do? So let's evaluate. Somehow my lecture notes is not well read. Okay, so let's consider the x-axis. X is equal to r is cosine phi. Y is equal to r sine phi. Okay, when r goes to infinity, y become constant. Okay, so those are the what we consider. So which means that the phi should be something like almost 0. So when r is equal to, okay, so phi is kind of like this phi. Yeah. So if phi is, I mean, the particles goes to infinity, phi becomes 0, almost 0. And then taking the okay, and then what we're going to happen is as follows. So if you take the derivative, so r goes to almost infinity, and take dd tau of this y is equal to 0 because it's constant, and take the r sine phi and dr and d tau, and then r squared d phi and the tau, and the cosine phi. So those are the equation you will get. You get by taking derivative with respect to so sorry. I think maybe I should write down the like this way, and then you can multiply. You can multiply r times r times r. Okay. So r times dy d tau is equal to r and r squared. Okay. That's what I did. Is it okay? Okay, so then we will use again the fact that the r squared d phi d tau is equal to L, and now dt or dr d tau is equal to minus square root to e. So okay, so this is what we have. So do you remember this one? Is it okay for you? Is it okay? Do you understand what this term is? How do you obtain this one? So we know that the one half r dot square plus b of r is equal to e, right? When r goes to infinity, this will become what? 0. So r goes to infinity, this is 0. Then if you take a square root, you have plus minus square root to e, right? Okay. And now we consider incoming particle instead of outcoming. Okay. So therefore, you should pick minus sign. Do you understand? So incoming r is decreasing. Okay. So that's why you get this one. And plug that one into here. Plug that one into here. So plug that into here, you get the R0 square root to E is equal to L. Okay. Fine. So I plug this one into here, then you get this. Is everything okay for you? And of course, I took phi goes to 0 limit. So here I also took phi goes to 0 limit. Phi goes to 0 limit. What's going to happen is what? Sorry, phi goes. But phi goes to, so this is kind of strange. So sorry, when you said phi go to 0, what's going to happen? This become 1, right? This becomes 0, right? So I'm cheating here. What's happening here is what? Sorry. I think I'm cheating here. I think, sorry, this is sine phi should be L times cosine phi. I think that should be the case. That should be the case. And then, how to determine the... Sorry, I got confused. Sorry. Let me do that computation. Sorry. Now I understand. Sorry, I understand. Sorry, it's okay. So I call this one y is equal to y r0 or y star. I call it y star. Sorry, I call it this is y star. So this is at infinity. At infinity, I fix this is y star. Constant is this is equal to y star. Okay. Then this part is y star. Okay. Because the y is this one. So y star, and then this is equal to square root 2e is equal to L. Okay? So do you agree with that? Is everything okay? Fine. Okay, and also I mean, if you have an infinite energy, so we take the limit to the e goes to infinity, e goes to the almost speed of light. So e goes to infinity. So this one is actually go to infinity, almost infinity. So everything goes to infinity. E goes to infinity, L goes to infinity in this case. Okay, so therefore, if you just use the equation, so L is equal to square root 3rg c. Then BR has the maximum, BR max, and then you have a BR. I mentioned that this is the R max, exist max, and then exist, and R min exist. So then one can compute R max. 1 over R max is equal to 1 over 3rg, and 1 plus square root 1 minus 3rg square c square L square. So that's what you get. Okay, what you get from this analysis. Then what we are going to do is that what we are going to do is that what was that? When L is go to infinity, so when L goes to infinity, so we take the infinite energy limit, infinite angular momentum limit, this becomes 1 over R max, and this part is gone. So therefore, is equal to 2 times 3rg. So therefore, R max is equal to 3rg divided by 2. Okay, so that's what you get. Okay, so then what we want to do is the condition of the E goes to so condition E goes to B max, B R max goes to 0, will go to will hit black hole. We hit black hole. So as I mentioned, that the if you have like this one, so this line is E is greater than B max, R max. And we want to evaluate this one. Then if you evaluate this one, so what you get is E plus c square over 3 minus 2, 27 rg L square is greater than 0. Okay, greater than 0, which can be written as this. And if you use the relation between these two, if you plug this one, if you plug this relation into here, what you get is that the E is equal to 1 minus 4 over 27 R0 over RG square and then plus c squared over q greater than 0. Okay, so that's the case. Okay, so in order to be this one to be positive, what we want is that definitely what we want is 27. Because I mean e goes to infinity, almost infinity, so this will be term will dominate. So therefore, what we want is the 27 over 4 divided by 4 should be greater than r0 squared. Okay, so that's what we get. Okay. Sorry, I shouldn't use r0. Sorry, I call it y star. I call it y star. Sorry. I mean, anyway, y star. Oh, I mean, I think bad name. My blackboard is bad name. My lecture is better. I call it R0 instead of y star. Sorry about it. Okay, so y star is less than this term, then eventually it hits black hole. Okay, do you understand? Because I mean, e goes to infinity, so therefore once this becomes negative, so this would definitely win against this second term. Okay. Okay. Fine. Okay, so therefore this is actually cross section. So if y star is less than square root 27 over 2 over times Rg, okay, then eventually absorbed into a black hole from this calculation. Is it okay? So therefore, if you plug that one into here, you get the 27 over 4 pi Rg squared. So this is a cross section. This is a cross section of black hole. So even if you take the infinite limit of energy of the particle, if the radius is this almost Schwarzschild, 20 square 27 is about what? Huh?
Should be shadow of the
5 point something, right? 5 square root 27 5 point something, right? Divided by 2 is 2 point something. Okay, that makes sense. Some 2 point some times Schwarzschild radius, even if you put the infinite energy, eventually captured by black hole. But that sounds reasonable estimate. Yeah. But otherwise, if you just, it depends on energy. It depends on energy. But if the energy is high enough, you can escape like this mode. Yeah, like this way, and so on. Maybe some particle may like us several times and move out of the black hole and so on. Okay, so this is a cross section of black hole. Any question at this moment? Okay, those are the just like making some kind of like extract some physics from out of the Schwarzschild geometry. Okay, let's move on. Now I'm going to talk about Burkhoff's theorem. I think it's a good pace. I think any question? It's too easy for you, maybe.
The shadow of the Schwarzschild electron is also that value. So is there any relation between two shadow values of the
Shadow?
Shadow values of the Schwarzschild electron is
This one.
square root of 3 times square root of 3. Exactly the same value. 3 times 3 times square root of 3, yeah. 3. Exactly the same, I mean, the value, the same value for y star.
Okay, so this one?
Yeah, that's
So this is equal to 3 square root 2, right?
3.
Ah, 3. Sorry. Eh? Oh yeah. Oh,
Yes.
divided by 2. Okay.
Yes,
Yeah.
Schwarzschild radius is 2m, so it is. So I mean, the shadow radius is exactly the same.
Yeah, yeah. So this means that it is the same calculation.
So my question is, what is the relation between the cross section of the black hole and shadow radius of the black hole?
Well, what's the definition of shadow? I don't know that. How do you define shadow?
Shadow. So when we observe the black hole, we will see the black area, right?
Okay.
The radius of the black area is called shadow radius of the black hole.
Ah, I see. So, but which means that they, yeah, the same thing.
But
But here we assume the particle is have a mass.
and you assume that also it has infinite energy, right?
So infinite energy goes to, so therefore the speed of light is close to the speed of light. So maybe I think if you do the same analysis with the light instead of particle, with a massless particle, then you will obtain the same.
Okay, we will get the same.
Yeah,
value.
yeah, should get the same. Yeah.
Yeah, it's photons.
Yeah, I think it's the same analysis. Yeah. Fine. So then let's move on. Or any other questions? So these are some kind of like just try to some making fun of, or I would say like enjoying the Schwarzschild geometry, and then now a little bit move on. So far we learned Schwarzschild and rational non-storm, which is we assume the static and spherical symmetry. One is okay. So rational non-storm. So the more general thing, rational non-storm solution, including which contains Schwarzschild of a black hole. When Q is equal to 0. Okay. So this one assumption is static, and then spherical symmetry. And then one is has the electromagnetic stress energy tensor. One is a vacuum. Okay, one is vacuum. Fine. And then so then you eventually get these solution. But the Birkhoff theorem states as follows. Birkhoff theorem is that if you only assume the spherical symmetry, symmetry plus a vacuum, then you get Schwarzschild. Which means that we don't need this one. We don't need static. That's the that's assumption. So to get the rational non-storm, you need a appropriately correction into the source energy. So T mu is appropriately defined appropriately defined. Defined. So which I'm going to omit because it's become complicated. So I will only focus on the first one, but you can generalize to the rational non-storm. So this means what? This means that if you assume we don't need static assumption. To get a Schwarzschild, we only need spherical symmetry in the vacuum. That's a kind of striking statement. So okay, before going to the proof, this means what? So if you have the something whatever, The Schwarzschild is just spherical geometry, spherical symmetry, and then the vacuum, which means that if spherical symmetry means that there is a if you have some S wave, so if you move there's a star here and move the radial direction, only radial direction in the homogeneous way, which means S wave. Okay, so you learn the S wave in the hydrogen wave function, right? So it's just only really spherical, symmetrically move. Okay, so so outside a vacuum, outside vacuum. So this is kind of some S-wave movement. Oh, stop. Outside a vacuum is the intact, or outside vacuum is intact. Does not know what's going to on in here. If it is an S-wave means it preserves spherical symmetry. Okay. Then even if the star move, whatever, how drastically you move in the S-wave way, the outside vacuum is intact. It doesn't know what's happening inside the star. Okay. So it's kind of like a kind of striking consequence.
You mean it will not emit gravitational waves?
Yeah, it doesn't emit the gravitational wave. Even though it's moving.
Yes.
Okay, so that's a striking consequence of the Boccaccio theorem, and let's prove that. It's very easy. We cannot detect anything.
But it is not true for electromagnetic waves, right?
Yeah, even rational Northstone case. Yeah, it doesn't. It doesn't. It doesn't. Let me think. At least electric field should be intact, but I'm not sure magnetic field.
If charges moves, it produces electromagnetic waves, so we should also.
If charges move, but I think according to Berkeley theorem, it shouldn't.
It all cancel each other.
Yeah,
right?
somehow. Yeah, somehow. It shouldn't. So that's why it's striking. Okay, to prove that, let's assume the metric is a general possible way with this assumption. Again, I restore somehow x0 square plus hrt dr square 2k rt. So spherical symmetry means that there is no such a term. Okay. Plus r rt, and then sorry. So it's okay. It's okay to have 2k rt and dt dx0. No, dr dx0, and then square. Okay, so this is an assumption, generic assumption for metric. So now we have the differences from the static case. Static case, we don't have this one. We don't have this dependence. We don't have this term. Okay, we didn't have this term. Okay, we didn't have this term. Okay, so this orange part is a difference from the previous assumption. Okay, and also here. Here also it's assumption. It's different. And you compute the metric. Okay, and then since it's a vacuum, so I again write down the Einstein equation. Einstein equation is a vacuum is equal to 0, which means that if you contract times G mu nu, we know this Ricci tensor should be 0. Okay, we know Ricci tensor should be 0, and if you plug that into here, this means that the R mu nu should be 0. So for vacuum Einstein equation, this should be 0. And compute the Ricci tensor from this metric. And what you end up with as follows. R0R is H dot, and then RH. So here, H dot is dH dt, and H prime is dH dr. Or maybe I should use D. Del. Okay. So this is equal to 0, means that the H is only function of R, not the T. So that's the main point. Okay, that's the main point. And the rest of the calculation is remains the same. Remains the same. I'm not gonna write down. I mean, it's the same evaluation. It's all the point is that the R00 and the R. So again R. So the rest of the calculation, if you use this fact, is all function of the can be written. It's the same as before, or the same as before. The same as before. Namely, it's a function, it's written rational function, namely, i.e., it's a rational function. Functions of f, h, and h prime, and f prime. So there is no dot up here. No f dot, no h dot. Okay. So all derivative with respect to r. Okay. So all with derivative. So we don't have this kind of term will show up in a Ricci tensor, even though we assume this kind of metric. And then if you do that again, R00 minus R equal to 0. Again, you get the f prime of f plus h prime over h is equal to 0, which means that the f of RT and h of R is equal to the function of t. Okay? Function of t. Okay? So this is so R00 R equal to 0, we get this one. And we know that the h is independent of t. Okay? So then, if f times h is independent of r, this equation will be satisfied. Okay? Will be satisfied. Okay? And then, what you get is that the so ds square is equal to minus h c of t. So all the dependence of f is restored inside of c of t. Okay? And push everything inside of c of t. And then h of r. H of r and dr square plus r square d omega 2 square. Okay. So that's what you will get. And then, so we can just redefine and the C of 1/2 dx0 is equal to dx0. So you just shift like this way. Then you can just obtain by the previous metric h of r c squared dt squared plus h of r dr squared plus r squared. It's very simple proof. Dr squared. Okay. So that's a rough way of proving this Burgos theorem. Okay. So that's the case. Anyway, so this means that this C of t, the dependence of t, f can depend on t, but it's just the artificial change of the defining time. So this means that it's just artificial. You can restore the t dependence in f, but it's just a redefinition of time. So that's what it means. Time coordinate. Fine. So those are the case of Burgos theorem. Then now, so okay, there's a fine. So we will move on to the. So again, as I mentioned, so a day after tomorrow on Sunday, it's not the holiday in China, so we will have the class, and then so we will cover a so-called cometric. Okay, so the car metric is kind of like a stationary space-time, and stationary space-time, which means that if you start with d square g00 d x0 square, and then 2c0i dx0, and then dxi plus gij of dxi, dxj, and so on. And those are independent of t. Independent of t. Okay. So those are not static but stationary. Okay. Stationary. So there is a difference between static and stationary, because there is some space-time will depend on the so-called angular momentum that will come from here. Okay, as we will see. Okay. So the space-time is kind of like has the dependence of angular momentum, and there are lots of interesting phenomena happen. I haven't written down. I finished writing up the note, unfortunately. I will do it immediately after this lecture and then tomorrow. Lots of things happen. So as you know, the most fascinating part is so-called ergosphere. Ergosphere. I will explain later. Ergosphere, and also so-called Penrose process. Penrose process, and also many things, so-called ring singularity, frame tracking, Many interesting phenomena, physical phenomena happen, plus so-called cross time-like curve, also superradiance, and some many interesting things we will see next time. So yeah, I think that would be the next lecture. So that's a curve black hole that has the angular momentum m and j, and if you put the Newman, you have angular mass and angular momentum and then charge. Okay, and so those, and then this one is the most generic black hole solution people can write down. So that's already theorem. So those are the exact solution we encounter. Exact black, more general exact black metric of the Einstein's equation, and which describes some black hole. Okay, so those are the maybe next lecture, and the coming like a two more lecture we would spend time on that, and then I think exact solution for cosmological exact solution is important. I think nobody's have learned the zeta and anti-zeta, so I will after that I will cover this cosmological exact solution. Maybe Friedman, Robertson, Walker, but those are kind of already learned, maybe many people. But the zeta and anti-zeta is worth exploring. Yeah, then move on to whatever, Keeling horizon, surface gravity, Raychaudhuri equation, singularity theorem, and so on. So those are the plan of this lecture. Okay, then let's see you tomorrow. Yeah, I think it's a good time to stop. Not tomorrow, a day after tomorrow.